Hello, welcome to another module in this massive open online course on estimation for wireless communication systems. So currently we are looking at the estimation of a vector parameter, and we try to motivate this in the context of a multiple antenna wireless communication system. So we said the estimation model for a multi-channel estimation in a multiple antenna wireless system. For instance, we were considering the downlink of a multiple antenna transmission system, considering multiple antennas at the base station and a single antenna at the mobile. So the estimation problem for this system can be written as, and that is what we had showed in the previous module, is that we have the model for multiple antenna channel estimation, which can be formulated as y1, y2, so on up to yn. Remember, these are the observations, that is equal to your pilot matrix, which has entries of the form x11 up to xm or xm1, x12 up to xm2. These are the pilot symbols transmitted at the second time instant, and x1n to xmn, this is your pilot matrix, times, let me write this a slightly different fashion, this is h1, h2 up to hm, which are the m channel coefficients, plus the noise samples, which are basically your V1, V2 up to Vn. So this is a system model for multiple antenna channel estimation, where y1, y2, yn, these are your y bar, this is the vector of n observations, this is the n cross 1, this is, let me write this clearly, this is your n cross 1 observation vector. This is the n cross m pilot matrix, that is the matrix of pilot symbols, and this basically, these are the unknown, this is the m cross 1 vector of unknown channel coefficients, and this is your n cross 1 additive noise vector, or simply noise vector. And then we had said this system model therefore can be written as your y bar or vector y equals x times h bar, which is the unknown channel vector or the parameter vector to be estimated, plus v bar, and so this is the parameter vector, correct. The parameter vector which has to be estimated. So we have y bar equals h x times h bar plus v bar, which h bar contains the m channel coefficients, the m unknown channel coefficients which have to be estimated. X is the matrix of pilot symbols, this is also known as the pilot matrix, correct. So x is known as, this is known as the pilot matrix. So, similar to what we have done before, we have to develop for estimation of the vector parameter h bar, we have to develop the likelihood function. So, any estimation we have to start by developing the likelihood function for the likelihood function corresponding to the parameter vector h bar. And again we will start with the same assumption, that is we will start by considering the noise samples V1, V2 up to Vn, the n noise samples to be IID Gaussian, to be independent identically distributed Gaussian random variables of mean 0 and variance sigma square each. So, consider V1, V2, Vn to be IID Gaussian RVs of mean 0 variance sigma square, which means the PDF of each, the probability density function of each noise sample Vk. What is this? This is the PDF. Let me write this again clearly a little bit. This is the PDF of each noise sample Vk equals 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square. In fact, since the mean is 0, Vk square, correct. So, this is 1 over, so this is the probability density function of each noise sample Vk, which we said is 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square times V square k, alright, because this is a Gaussian noise sample of mean 0 and variance sigma square. Further, realize now that all the noise samples are independent. Therefore, the joint probability density functions function of these noise samples V1, V2 up to Vn is the product of the individual probability density functions, and this is also something that we have seen before. Therefore, the joint probability density function, again just to follow joint PDF, again just to repeat it so as to be very clear, although many of you must be familiar, the joint PDF of V1, V2, Vn equals the product of the individual probability density functions f of V1, f of V2, so on until f of Vn, the joint PDF equals product of individual PDFs. Let us write this down. And why is this? Because since up to Vn are independent, these are independent random variables, and therefore, I can write this as basically 1 over under root 2 pi sigma square e raised to minus v square 1 by 2 sigma square times 1 over square root of 2 pi sigma square e raised to minus v square 2 by 2 sigma square, so on and so forth until 1 over square root of 2 pi sigma square e raised to minus v square n by 2 sigma square, which is basically equal to 1 over 2 pi square sigma square raised to the power of n by 2 e raised to minus 1 over 2 sigma square summation k equals 1 to n v square k. And what is this? This is basically your joint PDF. This is basically the, what is this? This is basically the joint PDF of the noise samples. This is basically the joint PDF of the noise samples V1, V2 up to Vn, but the noise samples are nothing but they are in the vector V bar, that is V1, V2, V bar, that is V bar, that is the noise vector, equals basically V1, V2 up to Vn. It is the n dimensional vector with elements V1, V2, Vn. Therefore, this can also be viewed as the multivariate density of these noise samples V1, V2, Vn, that is the multidimensional probability density function or the joint probability density function of V1, V2, Vn. Typically, this is also known as the multivariate density of the noise vector V bar. So, this is the probability density PDF of the noise vector or the multivariate PDF of noise vector V bar, which is nothing but basically this nothing but contains again the noise samples V1, V2 up to Vn. It is simply a different way of stating this. Now, if you observe this quantity, the essence lies in this quantity here, summation k equal to 1 to n V square n. Now, if you observe this quantity, now we know that our noise V bar equals V1 up to Vn. Therefore, if you now consider V bar transpose V bar, this is basically your row vector V1 up to Vn times your column vector V1 up to Vn, which you can now see is nothing but basically your summation k equals 1 to n V square k, and which is also basically norm of V bar square. Summation k equal to 1 V square k is basically nothing but V bar transpose times V bar, and it is also basically norm V bar square, where norm V bar is the norm of the vector or the Euclidean norm of the vector. Therefore, I can write this joint probability density function, that is this multivariate probability density function. In fact, I can now write this as the multivariate probability density function f of V bar equals 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square, the summation of V k square. I am going to replace this by norm of V bar square, and this is an important point. Notice that the summation is a small point, but it is fairly important. I am replacing the summation k equal to 1 to n V square k by norm V bar square, where norm V bar is the Euclidean norm of the vector or the L2, or also known as the L2 norm of the vector V bar. Now, once I replace this, now you can see basically, now go back to our system model, look at, go back to our system model. Our system model is our model is y bar equals x h bar plus v bar, which means, look at this, which implies basically bringing v bar onto this side, v bar equals y bar minus x h bar. So, one thing you can observe here is y bar is linearly related, or rather related in an affine fashion. Y bar is an affine function of V bar. Yeah, V bar is a Gaussian random vector. Y bar is basically simply a linear transformation plus some shift by a constant. If you have a linear transformation, it is a linear function, but this is linear transformation plus the shift by this quantity x times h bar. So, it is related in an affine fashion to this vector V bar, which is a Gaussian vector. So, Y bar is in turn, it is a Gaussian random variable. That is, if you take a scale, a Gaussian random variable, and you shift it by some constant, then what you get is basically a Gaussian random variable, correct. So, Y bar is also a Gaussian random variable, in fact a Gaussian random vector in this context, because it is a vector. So, Y bar is Gaussian in nature, and also observe that V bar is 0 mean. So, the mean of Y bar is x h bar. So, mean of Y bar or expected value, and we can look at this, the mean of Y bar equals x h bar. Now, therefore, what you can see is, if I use this relation V bar equals Y bar minus x h bar and substitute this in the multidimensional probability density function, I have f of, in fact I can write the probability joint probability density function as 1 over 2 pi sigma square e raised to minus 1 over 2 sigma square, and look at this norm, this V bar, I can replace it this by Y bar minus x h bar. So, what I am going to have over here is basically I am going to have Y bar minus x h bar square. This basically says Y bar is a Gaussian with mean x h bar, and this, now remember, this is the probability density function, but this probability density function, when I view it as a function of the unknown parameter vector h bar, this is now the likelihood function for the parameter vector h bar. So, this probability density function is now basically your for the parameter vector h bar, and I can denote this as similar to what we have been doing before, that is P of basically Y bar, which is your observation vector parameterized by h bar. This is the likelihood function P of the observations Y bar, this is the observations parameterized by the parameter vector h bar, the likelihood function of the observations Y bar parameterized by h bar, which is the parameter vector. So, this is the, just to be extra clear, this is your observation vector and this is your parameter vector. This is your parameter vector. Yeah. So, now what we have done is basically we achieved the aim which we initially set out for, that is to basically develop a likelihood function towards the estimation of this parameter vector h bar. And now, similar to what we have done before, we have the likelihood function. Now, we can consider taking the log, basically we can get the log likelihood function, which is more amenable to the process of estimation, right. That is what we said. So, the log likelihood function, that is, if you now look at again traversing exactly the same steps as we have done before, the log likelihood function, log likelihood function of the observation parameterized by the parameter vector h bar is nothing but the natural logarithm of the likelihood function of, that is P y bar semicolon h bar. Remember that semicolon plays an important role, which is now if you take the logarithm of the above likelihood function, you can see this is minus n by 2 natural logarithm of 2 pi sigma square minus 1 over 2 sigma square norm y bar minus x norm y bar minus x h bar whole square, correct. Okay. So, this is the log likelihood function corresponding to the parameter vector h bar, alright. We developed the likelihood function, taking the logarithm we get the log likelihood function. Now, we have to maximize this in order to obtain, we have to find the value of h bar, that is that vector h bar for which this log likelihood, the likelihood function or basically the log likelihood function is maximized, that is the maximum likelihood estimate of the parameter vector h bar. So, what I am going to do is I am going to maximize this log likelihood function, I am going to maximize this log likelihood function. But when you maximize this log likelihood function, you observe that this is a constant minus n by 2 log 2 pi sigma square. This 1 over 2 sigma square is also, this also is a constant. Again, once again observe that there is a negative sign here, basically that changes the negative sign. So, you remove the constant, you invert the negative. So, because of the negative sign, the maximization of the log likelihood basically you can see is equivalent to the minimization of this part. This is equivalent, that this is the symbol for equivalent, this is equivalent to minimizing norm y bar minus x h bar whole square, that is one can find the estimate, that is ML estimate, the ML estimate of h bar can be found by maximizing norm y bar minus x h bar square. Okay. And this basically, if you look at this quantity here, this is, look at this, this is basically norm of y bar minus x h bar whole square, that is basically the square of norm of the error y bar minus x h bar. This is the square of the norm of the error, and we are trying to find the h bar which yields the least squared norm of the error. So, h bar ML estimate, the ML estimate yields least square, that is the least square norm of the error. Therefore, this is frequently, this is very popular cost function, this is termed as your least squares, or let me write that in bold letters, this is termed as your least squares. This arises very frequently in practice, and this is termed as the least squares problem or the least squares cost, the least squares cost function. Right. So, this arises very frequently in practice, this is known as the least squares cost function, that is y bar minus h x bar y bar minus x h bar norm square. This is the norm square of the error, that is y bar minus x h bar, and we are trying to find the h bar which minimizes the norm square of this error, that is which finds the least squared, which finds that is the h bar which has the least squared error. This is known as the least squares problem. This cost function is known as the least squares cost function. Therefore, the ML, the maximum likelihood estimate of the channel vector h bar, is given as the solution of this least squares problem, and that is important to realize. So, colloquially, so ML estimate is solution to LS. Basically LS is the abbreviation of the least is solution of the least squares cost function or the least squares problem. All right. So, basically what we have done in today's module is basically we have started with this system model, this vector system model y bar equals x h bar plus v bar for channel estimation in this multiple antenna system. And then what we have developed is we have developed the joint probability density function for the noise samples. From that we have derived the Gaussian nature of the observation vector y bar, and we have also developed the likelihood function for this unknown parameter vector, likelihood function for the estimation of the unknown parameter vector h bar. And we have seen that maximizing the log likelihood is basically equivalent to minimizing norm of y bar minus x h bar square. This is known as the least squares cost function or the least squares problem, because it basically corresponds to finding the h bar which yields the least squared norm of the error y bar minus x h bar. All right. So, we have developed the likelihood function and basically formulated the least squares problem for estimation of the parameter vector h bar. In the subsequent modules, we are going to solve this least squares problem and actually compute the estimate of the parameter, the maximum likelihood estimate of the parameter vector h bar. So, we will stop this module here. Thank you very much.